Okay, this slide is a slide about finding the area of a circular sector. In this case, if you have a circular sector, such as this, given right here, and you want to find the area of that sector, you can find the area of that sector. Again, you must use radians. Very, very, very important. You cannot use degrees whenever you're doing any algebraic manipulation like this. To find the area of a circular sector, in this case, what you need to do is take the radius, square it, multiply by theta, and half that. So, for example, if we want to find the area of this sector given to us here, do you see that our radius is 8, theta is 80 degrees, and we want to find A. Or we can call that X, or we can just call it A. So, first thing we want to do is we can't use 80 degrees. We have to convert 80 degrees to radians. So if we take 80 degrees, since we're converting degrees to radians, we got to multiply by 180 degrees in the numerator, 180 in the denominator, pi radians in the numerator. Okay, so this reduces to 4 pi over 9 radians. So now that we have that, that is our theta. So if we just plug in what we know, A equals 1/2 times 8 squared times 4 pi over 9. If you plug that into your calculator, we're going to get 44.6 units squared. And if this radius was given to us in units, like for example if this was in inches, this would be inches squared. So why don't we go ahead and make that in inches. 44.6 inches squared would be the area of that sector. Okay, so now we're moving on to circular motion. That is a way of measuring the speed as something moves in a circular direction, like if you have, a rock on the tire of your car and you're driving down the street, how fast is that rock going in a circular direction? As it drives down the street, your linear speed is the speed of the rock as it's going down the street. Your angular speed is the speed of the rock as it's going around your tire. There's a very important formula that we're going to use a lot called V equals R omega. And this is a formula that you'll want to have memorized. It's a pretty simple formula, but it's one you'll use a whole lot. V is going to be your linear speed. Again, the speed of the rock. If you have a rock, I know this is a very random analogy, but if you have a rock on your tire and you're driving down the street, that rock is going around your tire really, really fast. The speed of that rock going around your tire is its angular speed. So that is omega. Then the speed that your rock is actually moving down the street is your linear speed, which is V. So the linear speed is always the radius multiplied by the angular speed. Okay, so we're going to apply that formula in our next slide here. Okay, so for example, if you have a question like this that says a ceiling fan with 16-inch blades rotates at 45 RPM. RPM represents revolutions per minute. So if we want to find the angular speed in radians per minute of that ceiling fan, what you need to do is take 45 revolutions per minute, and we basically what we want to do is convert revolutions per minute to radians per minute. So let's do a comparison. We need to cancel revolutions. So if we think about it, what is one revolution? One revolution is equivalent to 2 pi radians, right? Because 2 pi radians is a full rotation around the unit circle, a full revolution. So if we compare 45 revolutions per minute to 2 pi radians per revolution, do you see that revolutions canceled? And what are we left with? We're left with radians per minute, which is what we were looking for. So if we multiply that out, we end up with 90 pi radians per minute. Okay, so that is our angular speed. That is our omega. Now, if we want to find the linear speed of the tips of the blades in inches per minute, what we need to do now is let's think about this. We've got our ceiling fan. And these are the tips of the blades. We're trying to figure out how fast these blades are going in inches per minute. So we need to take omega, which is 90 pi radians per minute, and we need to convert radians per minute to inches per minute. Okay, so here is what you need to do. To convert radians per minute to inches per minute, anytime you have units of radians, remember, you can't even think of what radians are as a unit of measure, unit of length. That's because radians aren't really a unit of length. The way you can convert radians to a unit of length is just multiply any unit of length, such as inches or feet or meters or any kind of unit of length, by radians, and that will cancel the radians. So in this case, do you see that we've got a 16-inch radius of our ceiling fan? Because that ceiling fan has a 16-inch radius, if we multiply that radius, because remember our formula is V equals R omega, if we multiply the radius by omega, so 16 inches, this is omega, this is R, we should get V. And do you see when you multiply inches by radians, radians cancels and you're left with inches per minute. And if you multiply that out, you end up with 1440 pi inches per minute. So that would be the linear speed of the tips of the blades. Okay, next slide. We have a radial saw has a blade with a 6-inch radius. Suppose the blade spins at 1000 RPM. Okay, so what we need to do here is, again, to find the angular speed in radians per minute, we have 1000 revolutions per minute. Okay, the angular speed in revolutions per minute needs to be converted to radians per minute. So how can we convert revolutions to radians? 1 revolution is equal to 2 pi radians. Revolutions cancels and we're left with radians per minute. And if you multiply that out, you get 2000 pi radians per minute. And that would be the angular speed. That's your omega. Now, to find the linear speed of the saw teeth in feet per second, remember we use our formula V equals R omega. We have our omega, 2000 pi radians per minute. And we need to get our answer needs to be in feet per second. So we need to convert radians per minute to feet per second. So to convert radians to units of length, we need to multiply by a unit of length. 6-inch radius here. So if we multiply radians by 6 inches, and again, this is omega, this is R, so we've got V equals R omega. Now radians cancels and we're left with inches per minute. But we need to convert inches per minute to feet per second. So we need to convert inches to feet. So we have 12 inches in 1 foot. Now inches cancels. So now we have feet per minute, but we need feet per second. So now we need to convert minutes to seconds. We know that there is, in 1 minute, there are 60 seconds. And now minutes cancels and we're left with feet per second. So all we have to do at this point now is plug it all into our calculator. we plug in 2,000 times pi times 6 divided by 12 divided by 60. And if you plug all that in correctly, you should get 2.09 feet per second. No, I'm sorry. That's wrong. You should get 52.3 feet per second. Remember, when you're doing analysis like this, you multiply everything in the top, you divide everything in the bottom. It's real simple. 2,000 times pi times 6 divided by 12 divided by 60. Okay, so now moving on to the next slide. Last slide here for 6.1. It says refer to problem 69 in your book on page 482. So if you look in that at that problem, it says to measure the speed of a current, scientists place a paddle wheel in the stream and observe the rate at which it rotates. If the paddle wheel has a radius of 0.2 meters and it rotates at 100 RPM, find the speed of the current in meters per second. Okay, so it rotates, its radius is 0.2 meters, and it rotates at 100 revolutions per minute. We need to find, our answer needs to be, we need to find the speed of the current in meters per second. That needs to be our answer. So let's start off with 100 revolutions per minute. We need to end up with meters per second. So let's just think about what we know and what we don't know. Okay, first we need to get our omega, our angular speed. So to get our omega, we need to take revolutions per minute, convert that to radians per minute. So 1 revolution is equal to 2 pi radians. Revolutions cancel, and you get 200 pi radians per minute. Or actually, let's not even do that. Okay. Now, we've got radians per minute. We need to end up with meters per second. So, to convert radians to units of length, remember, we need to be able to multiply by some unit of length. And do you see that our radius is 0.2 meters? So if we say 0.2 meters here, radians cancel. Now we've got meters per minute, but we need our answer to be in meters per second. So to get our answer into meters per second, what we need to do is convert minutes to seconds. So 1 minute is equal to 60 seconds. Now minutes cancel, and we have meters per second. And you should end up with 2.09 meters per second. Okay, if that way doesn't make sense to you and you like using the formulas, what you could do is first find your omega. Omega is always going to be 100 revolutions per minute times 2 pi radians per 1 revolution. And your omega comes to be 200 pi radians per minute. And then we want to use V equals R omega, which is going to be the speed of the current, the linear speed. Now that we found our omega, we just say V equals R, or we'll take our omega, 200 pi radians per minute, and multiply that by R, which in this case is 0.2 meters. And you see that that gives us our answer in meters per minute, but that's when we need to convert meters per minute to meters per second. So we multiply by 1 minute over 60 seconds, which gives us 2.09 meters per second. Okay.